restricted to a plane, it's sufficient for us to consider braiding particles. So think of this as like a counterclockwise twist, two particles like that, or the inverse. And the third thing is fusion. So given two particles, I can bring them together, and they'll turn into one particle. So it could turn out that what they turn into is the vacuum, so they annihilate. And I'll just erase that. And actually in this talk, that's really the only kind of splitting and fusion that I'll consider. And really, it's going to be all about the braiding.
These are dynamical projectors.
These are dynamical projectors, right. So in these theories, you can ask the question, well, what's the probability for a certain process to happen? Where let's say I create a couple of particle-antiparticle pairs from the vacuum. Then I move them around, and braid in various ways. And then at the end of the day, I bring some neighbors back together again. And I see if they fuse to the vacuum. So let's write this process where they all fuse back to the vacuum like this. And I know I have some other like that. We can ask, what's the probability that this happens? And by this happening, I mean, so there's no indeterminacy up here, but at the bottom, where I try to fuse these, and these, they might turn into some other particle. And I just want to know if they don't. So it turns out that this probability, all it depends on is the topology of the world lines of these particles in 2 + 1 dimensions, or in R3. And by that, so it's a topological invariant, meaning that the probability should be the same for this process. And it winds up being proportional to something called the Jones polynomial of the trajectory or link in 3 dimensions, evaluated at a certain value of q. Q equals a root of unity, e to the 2 pi I over k plus 2, where k is this k up here. And so I said it's a link. Well, formally, what's a link? Well, mathematically, a link is a smooth embedding of some collection of disjoint circles into R3 in such a way that they don't intersect. And we can define it. Yeah,
So is the Jones polynomial about evaluated root of unity actually a non-negative real number?
No. So, okay. That's what I said. And so we can define an equivalence relation on links, saying that 2 links are equivalent, or to use a fancy word, isotopic, if one can be continuously deformed into the other without crossing any strands through each other. So, just as an example, this here is, I didn't prepare an example, so I can sit here and try to figure it out, but I don't want to get so, you know what I mean? Well, I crossed it through, so I think, oh, it is the unknown, great. So then that was the unknown.
Yes.
Perfect. Okay. Or even, I could have done it like this. I'll say this is equivalent. So the Jones polynomial is an invariant of links, which means that if I describe 2 links to you, I should be able to compute, at least in principle, this polynomial, j of q, which is actually a polynomial in q to the plus minus half in integer coefficients. Such that if 2 links that I've described are equivalent, they have the same value of this Jones polynomial. So it's also a topological invariant in the same way that this probability here is. So how are we going to describe links? Well, for the purposes of this talk, we'll really think of links as closed braids. So the idea is that we'll take something called the braid group, and this thing here is just going to be the you can think of it as configurations of n hanging pieces of string, tied at the top and tied at the bottom. And the idea is that they can be twisted around. Like this. And it's a group because I can compose two braids by stacking them vertically. So I can put another braid down here, and that's the multiplication. So you can write this formally using generators and relations, but we don't really need to do that. just know that the two, you have equality in the group if you have isotopy when you embed it into R. And intuitively, this makes sense. So let's see. Right, so we're going to close these braids and turn them into links. Well, how can we do it? So I'll focus on two in this talk. One we'll call the plat closure, or what I'll do is I'll take neighboring guys here and I'll connect them like this. And I'll write that if this was a braid, E, I'll say that the plat closure, I'll just draw little things like that to remind you that's what we're doing. Another way you could close it is what we'll call the trace closure. And there, you take each guy and you connect it down to its friend on the bottom, like this. And you can think of both of these as physical processes, where what you do is you create a particle-antiparticle pair right here, and in the case of the trace closure, you just take half of those guys, you braid them, and then you re-annihilate them with wherever they're sitting on the bottom. For the plat closure, it's similar. You just braid all the guys, and then you see if they annihilate with the neighbors on the bottom. So, and we'll use these two different methods of describing links via braids to give two different definitions of the Jones polynomial for these types of closed braids. And so these definitions are going to be based on representation theory of the braid group, and in a related way, the theory of quantum groups. And so what's a quantum group? I'm not really going to tell you too much, but I'll tell you it's not a group and it's not really quantum. But you can, I mean, roughly they're like a family of generalizations of some Lie group, like SU2, that are parameterized by some variable Q. And you can either think of Q as a formal variable, in which case you actually would wind up deriving this polynomial as a polynomial in a formal variable, or you can think of it as a complex number. And in that case, it's like evaluating this guy at a certain number. And in particular, we're going to think about it as this number right here. But the thing about this family of deformations is that as Q goes to 1, that you should get back the usual structure of the group. And we'll see that in action. So, essentially this relation that's going to define the Jones polynomial is a generalization of a fundamental duality between, say, SU2 and the symmetric group Sn on n letters. And that's known as Schur duality. So let's start there, and I'll recap some of the basics of what we need to know from there. So, if you take SU2, its irreducible representations are given by spins. So they're the form J equals lambda to the half, where lambda is some natural number. So 0, a half, 1, 3 halves, and as large as you want to go. And so I'll write these representations as little v, big V. So big V will be the vector space, and little v will be, say, a map from SU2 to, in this case, the unitaries on the space. And so these have the property that the dimension of V lambda equals lambda plus 1. Okay. So, so as with any group, if you take two representations, I can tensor product them together, and I get a new representation, say V lambda tensor V mu, and I can also direct something. I can take V lambda, direct something. And the idea is that this representation here takes a matrix U, and it maps it to just the tensor product of these matrices, the one for each dimension, or for each representation, and the total dimension is the product of the dimensions of these guys. Whereas this here, what it does is it creates a block diagonal matrix, like V lambda U, V mu, U. So it's always the same U in both spots, and the same U here. And the dimension here is the sum of the dimensions. But just to do an example, let's consider V1, which we'll call, this is the fundamental relation, or representation, or the defining representation, and then it's two-dimensional. And really just V1 of U equals U, acting on space in the normal way. And let's say that I consider V1 tensor V1 now. Okay? So here, it turns out that this space, by a unitary isomorphism, is equivalent to V0 direct sum with V2, or the spin 1 and the spin 0 representations. So in the sense of unitaries, if I take U tensor U and apply this same unitary, what I then get is a matrix that's block diagonal. The top block will be 1. These are special unitary matrices that are determining 1. And then I'll get a 3 by 3 matrix in this block. Okay. So, but there's also another representation that acts on this space, namely that of S2, the symmetric group on 2 letters.
Is that B2 with you, or?
Yes. Spin 1, B2. And so this group here has 2 elements. It's the identity and the transposition that swaps 1 and 2. So let's define a representation of this on our tensor space right here that just swaps the tensor factors. Okay, so for example, so I'll call this representation R, and R of this transposition 1, 2, acting on like these 2 states just swap. Okay. So turns out that this, and so the other guy's the identity, we'll ignore that. But this matrix here commutes with every matrix of this form. So for all U, right, because it's block diagonal here. And what happens is, so let's look at the basis here and see what it does for each one. So for this block here, it's just going to give me this state. Say 0, 1, minus 1, 0. Spin sigma state. And for this block here, what's going to give me is 0, 0, 0, 1 plus 1, 0, and 1, 1. So these are the triplet states. Okay? And if you look what happens when you swap the 2 tensor factors, well, with these guys, nothing happens. They stay the same. So this is the symmetric subspace of these 2 spins. Whereas this guy here, if you swap them, it picks up a -1, so it's the antisymmetric subspace. And so these 2 are both irreducible representations of SU2, the trivial and the sign representation. So, what we've basically found, let's move over here, is that, in somewhat fancy language, the endomorphisms that commute with SU2, we didn't really find this, but it's true. Basically, these are the only guys that commute with the action of U tensor U. But these guys here are isomorphic to, say, linear combinations of the identity matrix and the swap key. And this, in turn, is just isomorphic to the group algebra of S2. So basically, these permutation matrices give you everything that commutes with U tensor U. And also, U tensor U is everything that commutes with the permutations. So we say that these are sort of in a dual relationship, and this is known as Schur-Weil duality or Schur duality. So how can we generalize this? So we have a general rule for tensor producting. If I take V lambda, tensor V1, defining representation, we know that this is just, you go down 1, and you go up 1. So like a spin 1 tensor spin 1/2 is a 3/2 and a 1/2, and so on and so forth. So we can encode this rule in a graph. Right, so it's very part of it, because it's infinite. And 0. So this would be lambda here. And here I'll put n down here. 1, 2, 3, 4. And the idea is that each time you tensor, so if I have a spin 0 and I tensor with a spin 1, I get a spin 1 only. If I tensor again with a spin 1, or sorry, with a spin 1/2, lambda 1, I get a 2, or I get a 0, or a 2. And this continues. And it just goes on forever. And so these 1, 2, 3, 4, 6, 8. And so you can see if I'm sitting here, if I've got a spin 2 guy, well, okay, let me back up and say a little more about what this is. So let's say I consider V1 tensor 3 times, right? So I start here, here's the first tensor, it puts me at a 1. If I tensor in the second guy, it gives me a 2 and a 0. But then when I tensor a third time, I can get contribution of this guy here, the 3, and this guy here, the 1. But notice there's two ways to get to the 1. I could go up here and down, or I could go this way here. So it turns out that using this graph, what we show is that this tensor product is isomorphic to V1 tensor C2. There's a multiplicity in the decomposition. And you also get a V3 in 3/2 representation. And maybe I'll just write in tensor C. It's the same thing. So, right, so in general, maybe I'll just write this up here, because this is extra important. If I do this n times, I get this fundamental formula. So, the idea is that these guys here are SU2 representations, irreducible representations, and these are irreducible representations of the symmetric group. And so what does this mean? This means that if I take U tensor n, and if I do this unitary change of basis here, that this is just the direct sum over lambda of, let's say, little v lambda u tensor some identities on these R lambdas. And if I look at this representation that permutes the tensor factors for any permutation P, this is going to be the same thing, except now the identities go over here times this representation R of P. So this makes it evident that these two guys commute with each other, and also that they're essentially the largest things that commute with each other. So what do these representations look like? These R lambdas here. So I'm not going to just worry about too much about what these look like. These are more relevant for describing the Bray group representations that we care about. So the symmetric group is generated by swaps of transpositions, local transpositions. So say, I'll call these P sub I, which are just the guys that swap the tensor factor I and I plus 1. So it's sufficient to define these representations just on these generators. And so you multiply just by, so I can draw diagrams like this, where this is I plus 1, and then I can take another guy here. So this would be, say, Pi plus 1, I, so like this. And so one thing I didn't mention is that what's the dimension of this guy here? Maybe it was implicit from this diagram, but the dimension is the number of paths it takes to get you to that label of length n. So we saw here, there's 2 paths to get me to here. And this representation here is 2-dimensional. Because there's 2 paths that get me to 1. But for 3, there's only 1 path that gets me there, which is why this guy was 1-dimensional. So that means that there should be some basis that's in bijection with the set of paths. And in fact, there is. So what we can do is we'll just define this basis. Let's see. Yeah, so we'll say that this R lambda n equals the span of paths. Start from 0, go to lambda 1, where lambda n equals lambda. Okay, so now it's really easy to see what the structure of these transpositions are going to be. And I'm not going to tell you the numbers that come out. But, and I can actually define them for all the representations simultaneously. I don't have to put lambda here. And what it does is this, is that, so let's say I'm going to do the ith transposition. So this acts essentially locally on the path. So let's say the path looks like this, where this is I minus 1 plus 1. That is basically just going to give me a linear combination of the same path, like this, plus the same path where I took this guy down, and everything else stays the same. And so defining it just locally like this defines it on all the paths. And if it turned out that it didn't bend, that it was going like this, well then it's just going to be some other constant lambda, like that. And similarly for going down, and from these ones here you can define what happens on the other one by unitary.
Are the paths orthogonal?
Yes. Yes. So this is called Young's orthogonal representations of the symmetric group.
But where are you using the permutation?
Because I'm going to generalize this to the break group, and it has a very similar structure. So I thought it'd be easier on everybody to do it this way. Where am I using it?
Where are you using it in this equation?
Well, I'm using it up here. I'm defining this sort of fundamental relationship between the unitary group and the break group. And then I'm going to generalize this. But I just thought this would be an easier place to start. So it's sort of abstract. It's not that physical yet. So one thing I should mention is that these numbers here, that they're all functions of basically the values of this path. So lambda I minus 1, lambda I, and lambda I plus 1. And that's it. So what this means is that there's basically a block diagonal structure for each one of these guys. So if I look at R, for Sn, acting on some permutation or transposition Pi, but I can write this as a block diagonal matrix in the basis of paths. And it's just going to either have 1 by 1 or 2 by 2 blocks, according to whether you're in this case or this case here. So just block. And it'll be different for each one. But it's sort of nice to know, because it's easy to define them this way, or to understand the structure. So that's all I wanted to say about the non-deformed case. So, how much time do I have?
20 minutes.
Oh, okay.
Is that enough?
Yeah. I was hoping to finish even earlier.
In that case, you have 15 minutes.
Okay. So now we're going to Q deform, okay? So here what we do is we take SU2 goes to some quantum group. Call that SU2, okay? And symmetric group goes to the break group. And so here this should be Q equal 1. Over here this will be Q equals e to the 2 pi I over k. And so what changes? Well, for our purposes, the main thing that changes is that the representation theory gets truncated. And I really wish I didn't erase this diagram, because I'll draw it real fast again. So before this diagram went up forever, now we're going to cut it off at 0, 1, 2, 3, at k. And then it stops. And this is because we only have a finite number of particle types. And the particle types essentially correspond to representations of SU2 in sort of the standard quantum field theory way, right? Particles live in representations of some symmetry group. So here it's not something complicated like the twin Bray group. It's just a quantum group. But so let's see. Right. So what happens when you truncate this is that basically your tensor product starts to fail. Right. So how do I define VK tensor V1? Well, before this was VK plus 1 plus VK minus 1. But now this guy doesn't exist, so let's just throw it out. And let's define this to be a new tensor product, truncated tensor product, which I'll put a hat above. So now this is going to screw some things up though. Like for instance, if I look at the dimension of say V lambda tensor V mu, then this does not equal the product of the dimensions of the individual guys. So should this really bother us or not? I mean, I don't know, but there's a nice thing that comes into play here that essentially helps us out. You can define a number for each representation called the quantum dimension. So find that dim Q, and it turns out that for, say, the representation V lambda, this equals what we would call a quantum integer, lambda plus 1. And in general, you can define these. It's something like sine pi I don't expect you to remember that, but it's maybe easier to just notice for the defining representation. what it's going to be is this, which is just 2 cosine pi over the root of unity, k plus 2. So in particular, it's always less than the real dimension.
Is that obtained as a trace of an identity?
Yeah, it's a categorical trace.
Yeah.
And right, so this quantum dimension, it turns out, does have all the nice properties that you want. So I won't write it, but I'll just say the quantum dimension of the tensor product is the product of the quantum dimensions, and if you take a direct sum, you add them, and as it turns out, these are algebraic integers, so they form a ring. But let me just give some examples for some of the things that we've seen already. So what are they for when k equals 2, which corresponds to q equals 4th root of unity I? Well, this is what Prakash mentioned before, these Ising anyons. And basically you have, say, lambda equals 0, 1, and 2 are the only particles. And their quantum dimensions are 1, square root of 2, and 1 again. And another interesting case is when k equals 3. What you get 0, 1, 2, 3 particle labels, and their quantum dimensions being 1. The golden ratio again, and 1. So this is another reason that Fibonacci anyons are called Fibonacci anyons. But really, for the Fibonacci anyons, you're only picking this particle and this one. This is kind of like the relation between SO3 and SU2, that you only have integer spin representations. So, or in the case of these labels, you have only even labels. So, see, one last thing I should mention about quantum dimension that's nice is that if you just look at the ordinary dimension of something like, you know, the nth tensor or truncated tensor product, the large n, that this is approximately, or tends to in the limit, the quantum dimension of the n power. So it kind of tells you the asymptotic rate of growth of having, say, n of these types of anyons. So I think Eric mentioned this at the end of his talk. This is what the system Hilbert space grows like asymptotically. So, okay, so I'm almost done. I'll almost be able to tell you what the Jones polynomial finally is.
What's the connection with this, the grade group?
Right, so that's the next thing I'm going to do. I'm going to define what these representations
Checking
are.
before you rub it off.
Right. I'll try to decide what I should be. Maybe I'll just, I think I can just say it. I mean, so the idea is that we have a, well, we all write. So let's make this a truncated tensor product now, and think of this as the defining quantum group representation. Up here, you're now going to cut off at the minimum of n and this level of k, because you can't have any more possible dots here. And basically, it's just going to look the same. So this will be here, and these will be bn here. So the connection is that since I then truncated my diagram here, say I stopped it at 1, 2, 3, right? So it's just going to go on like that. That basically, these Gray group representations now are just spanned by paths that stay on this diagram. And essentially, the equations are exactly the same, at least in the combinatorial structure, and these constants are different. And in a sense, if you write down the symmetric group representations, you have all these things like square root of some number times another number over another one. And literally what you do is you turn them into quantum integers, at least for the Jones polynomial. That's how it works. Or for SU2 level K. And yeah, so now I'm almost there. So let's say that I've got some operator that commutes with the action of this quantum group thing, acting on the tensor product space, or truncated tensor product. So by the shear duality, basically, it's just going to act over here. So it'll be of the form direct sum over lambda. Sorry, identity on v lambda. Tensor sum O lambda. And I can define something called a quantum trace of this operator then, which is just going to equal sum over lambda of, see, the quantum trace of this guy, which turns out it's going to be its quantum dimension. So, times the ordinary trace of this thing here. So, just the usual trace. Okay. So, now back to the Jones polynomial. So the Jones polynomial, the trace closure, can essentially be written as a quantum trace. And why is that? It's because these break group representations, they satisfy this. They commute with the quantum group action. And at least their absolute values are equal to this. So just to write it. So the Jones polynomial of the trace closure of a braid evaluated at one of these roots of unity, its absolute value, let's square it while we're at it, is equal to the quantum trace of this braid group representation of the braid that you're closing. And this is just a weighted sum of traces. I have a plus 1, usual trace of this braid group representation, like that. And how about for the Platt closure? Well, it turns out it's even easier. All you need to do is you look at a particular matrix element of one of the irreps. So I take the Platt closure. I have e to the 2 pi. There's some really big, exponentially big normalization factor that comes in for certain reasons. And I'll describe that like this. Say the 0 one. So this is the guy that's spanned by all the paths that come down to the lowest level after n steps. And so by this, I mean the path that goes 0, 1, 0, 1, 0, 1. Okay? And so this probability of one of these processes happening, i.e. of the particles tracing out a link in 3 dimensions, is given by either the trace or the Platt closure, is given by a normalized version of one of these guys. And how can we see what that normalization is? Well, you just want to make it so that this is a probability, both between 0 and 1. And basically, the largest value that the Jones polynomial can take out of root of unity can, by unitarity, which I didn't tell you, but these representations are actually unitary at roots of unity. It's important. But by unitarity, you can show that it's basically going to be greatest when you have as many disjoint unknots as you can possibly have. So for the trace closure, if you have n strands, you can almost have n unknots. You can also show that the Jones polynomial of a single unknot, or of n unknots, is just quantum 2 raised to the nth power. And for the Platt closure, basically I have, in this case I have 6 strands, so you need an even number of strands. So I can have n over 2 maybe. So I can just get rid of this, and I can put in here a 1 over quantum 2 to the n. And this would be the probability for the processes happening. So I think I'll stop there.
Our prediction blew me away.
Let's go swimming.
Serious?
About the time. Let's go.
Too slow, man.
Well, I thought there was going to be questions, so I was like, alright, if people ask a question, I'll get up and I'll,
Run.
well, you run. I need someone to run in front of me. They're just going to be running. Yeah. What? Yeah? Yeah, better. Get in there, Russ. Sweet.